Hi everyone. In this video, we are going to cover section 4.7, Applied Optimization Problems. On the next slide, I will have a procedural set of steps that will follow as we solve these lovely word problems that you're all going to love so much. But for now, this first problem, I just kind of want to walk you through the structure, what to expect from them before giving you the rote set of steps. So if you want to pause the video and read what we're going to do in this problem, go ahead and do that. Okay, assuming that you already did, let's take a look. We have a rectangular garden. You can see a picture of it below. It's beautiful. And it has a rock wall on one side. That's important. And we're putting wire fencing on the other three sides. Hey, that sounds like perimeter. We have 100 feet of wire fencing that we're putting around three sides of the garden. Okay, so if you want to add that to this beautiful flower garden picture, we have these three sides are all getting wire fencing like that. And then it says determine the dimensions that would create a garden of, and here's the really important part, maximum area. So in these problems, you will always have what we call an objective function that you are trying to optimize. That is the area. Okay, so we want maximum area. All right, and we can already write down a formula for area of a rectangle. A equals xy. Look at that. Area of that rectangular garden, length times width, base times height. I'm going to use an x and a y. And in these problems, we are also always given what is called a constraint. Constraint. Okay, in this case, that constraint is the perimeter. We have exactly 100 feet of wire fencing. That is all that we have, no more, with which to maximize the area of our flower garden. Now, I already wrote x and y, but let me just add my x and my y to this picture. So those two sides would be x, and this side would be y, because again, it is a rectangular garden. So our constraint in this case is that the perimeter of this rectangle, but only the three sides, because we have that lovely rock wall that we already bought last year, the constraint is that 2x plus y is equal to 100 feet of fencing. All right, so that is the setup for the two functions, the two equations that we're going to work with here. And then the next step is to take that constraint and use it to rewrite my area function in terms of one variable. And then in order to optimize it, in order to maximize the area, we're going to take the derivative, set it equal to 0, and find a critical point. Hey, that should sound familiar. Okay, so my next step, I'm going to take my constraint and solve for y, subtract 2x from both sides, and then that we substitute into our area function. Area is equal to x times negative 2x plus 100. So that would be negative 2x squared plus 100x. So I want to find now the maximum area. In order to find a maximum point on a function or a minimum point, we take the derivative, set it equal to 0 to find a critical point. So let's do that. A prime is negative 4x to the first power plus 100. And then we'll go, all right, set that equal to 0. Let me scroll up a little bit here. All right, so we add the 4x to both sides. 4x is equal to 100. Divide by 4. Find that x is equal to 25. All right, so then the next step is we can write down what our dimensions for our garden are. If x is equal to 25, then let's change to red here. Y is equal to negative 2 times 25 plus 100. That would be negative 50 plus 100 is positive 50. So our dimensions to maximize area are 25 feet on the x side by 50 feet on the y side, and that's going to enclose as much area as possible inside of that garden. Because I didn't have to do 25 by 50, I could have done 10 feet on x, 10 and 10, and then 80 for y. but that area would be smaller. That's what the argument here is, and you can check that if you want to. If it were 10 by 80, the area would be smaller than 25 by 50. I could also do x is 20 plus 20 is 40, then the y would have to be 60. But again, that area, that base times height, would be smaller than 25 by 50. And now how do I know that that area that I just found, or those dimensions that I just found are a maximum? Well, using my second derivative, a double prime is equal to just -4. Okay, and that tells me that that function is concave downward. Remember this from last section, or 2 sections ago maybe. That tells me that we are concave downward, right? And if my second derivative test were concave downward, that point must be a maximum. All right, so that's like the verification that what we've found is a max and not like by chance a minimum point. All right, so that's kind of the overview of what we're going to do in this section. And I'll go through a couple more sample problems after giving you the formal steps to follow. Okay, so you should pause the video and read through the 6 steps and maybe even go back to the previous problem and kind of look at them side by side and see when I followed each of those 6 steps. I'll briefly say them. We're going to figure out what our variables are in the last problem, x and y, draw a picture or we'll be given one, determine what are we maximizing or minimizing, write a formula for that quantity that we're maximizing or minimizing, and then write any equations relating the independent variables from step 3. So that was the constraint that I talked about. The perimeter, we were limited by this amount of fencing. The domain of consideration, now I didn't formally state that in the last problem, but we couldn't have had any negative values. The length and the width had to be something between 0 and 100. And then locate our max mins from step 4. This step involves looking for critical points. Okay, so those are the steps, and let's do that with this next example. We have an open top box being made from a 24 by 36 piece of cardboard, and here's the tricky part to when we draw the picture, by removing a square from each corner of the box and folding up the flaps on the side. And it says what size square should be cut out of the corner to get a box with, hey, there's a really important maximum volume. Okay, so we are maximizing the volume of a box. Now, the first thing that I want to do with this one is try to get an idea visually of what's going on here. And it says we have a piece of cardboard that is 24 by 36. So rectangular piece of cardboard, 24 inches there, 36 inches there. And then we're removing a square from each corner. So we're cutting out a square on each of the 4 corners. Those would all be identical squares, even though my picture doesn't really look like they are. That's getting cut out. And then we're folding up the remaining 4 sides. And you could see how that would kind of make a box with an open top. Hopefully you can kind of see that. All right. So what I want to do is add to my picture the length of each of those sides is x. Each of the sides of the square that I'm cutting off, we're going to call that x. So the next thing I want to do is I'm going to write down what I'm maximizing, which in this case is volume. And I know the volume of a box is length times width times height. Now I'm just going to need to substitute something in terms of the variables for this problem for the L, the W, and the H. Okay, and that comes from actually folding up those sides. All right, so when I crease and fold up this bottom edge, this side, and that side. And if you want to open up OpenStax and have it side by side, they have a better 3D picture than anything that I could produce. So that would be beneficial to pull up right now. Okay, but what we can see is that this bottom piece of the box and this top piece of the box are both shorter than the 24 inches, right? And how much shorter? Well, I took off this x distance and that x distance. Okay, so the constraint here comes from the piece of cardboard being 24 by 36. That helps me to substitute in for the length. The length is 24 minus 2x. Now, some of you might call that the width. It doesn't really matter. It's just the first one that I figured out. And then the width, the other dimension of the bottom of the box, this distance is shorter than 36 inches. How much shorter? Well, I took off this x and I took off that x. So the width of the box is 36 minus 2x. Okay, lastly, the height of the box, if I fold up those two, this flap here, the height of the box is just x. Okay, so here the constraint wasn't really a separate equation, but we were constrained by the dimensions of the cardboard that we're using, the piece of cardboard. All right, now we have our volume function with everything plugged in. So the next step is going to be to write that in a way that we can take the derivative. Now I could do this using like the super product rule, but that sounds terrible. So let's expand this out first. V equals, what you end up with if you distribute all this is 4x to the third power minus 120x squared plus 864x to the first power. So I'm going to take the derivative of that, 12x squared minus 240x to the first power plus 864. And then I want to set that, oops, that's the derivative, forgot my prime. And then I want to set that equal to 0 and solve for my x's. Now, luckily, every term in that equation is divisible by 12. So if I, let me just write it out with a different color. If I divide everything through by 12, what we get is x squared minus 20x plus 72 equals 0, which looks like one that I could factor, and you can try to find the factors of 72 that will get you 20. You're not going to get there, so what do? Quadratic formula. All right, I'm not going to go through the quadratic formula. If you want to look at those steps in OpenStax, feel free to do so, but I'm just going to jump right to the two solutions. X is equal to 10 plus or minus 2 times the square root of 7. And now I want to type these two into my calculator and see what they are in decimal form. Now 10 plus the square root of 7, if I do the positive root, is approximately 15.29. And then if I change that plus sign to a minus sign, we get 4.71. Now, we get to throw out one of those answers. And again, here's a part where you can pause the video and see if you can figure out which one gets thrown out and why. And if you've unpaused now, 15.29, that gets thrown out. That is not in the domain of consideration, is the fancy formal way to say it. Because if x were 15.29, then how do I cut that off of this side? How do I cut 15 inches plus 15 inches equals 30.6-ish inches, right? That doesn't work. I can't cut that off of that piece, that side of the box. So the only possible x that will work here is x equals 10 minus 2 times the square root of 7, which is approximately 4.71 inches. And that's what it asks. What size square, right? That's the size of the square that I'm going to cut off of each corner. And then when I fold it up, the box has the biggest volume that it possibly could. And if you want to substitute that x back into the volume equation, you can figure out what the volume, the maximum volume is. But that's how you would do it. Now we'll look at our last example of this section. We have a rectangular box. That's important. It has a square base. I'll mention what that means in a little bit. And an open top and a volume of 216 cubic inches. So they're throwing 4 things at you in the first part of the sentence, or in the first sentence. And then the second sentence tells me what we are optimizing. We are trying to build a box that has a minimized, as small as possible, surface area, as small of a surface area as possible. And then it also asks, what is that minimum surface area? So once we have a solution, we also have to find out what that surface area is. So let's go through the steps. First thing, let's draw a picture. So I'm going to draw a rectangular box that has a square base. So first I need a halfway decent three-dimensional box. I think I did okay there. All right, so the significance of a square base tells me that I can label the bottom of the box as x by x. Normally a box has three dimensions, length, width, and height, x, y, and z. But because this one has a square base, it's going to make it more doable for our skill set. Okay, it doesn't have to in real problems, but it makes it easier for us to go through. I do not know how tall the box is. So it's x by y. Those are the three dimensions. So we can write down our constraint, our volume equation, v equals x squared y. But the volume is 216 cubic inches. I'm not writing v equals for this one because normally I just try to write that v equals if I'm trying to maximize the volume. Okay, here we're minimizing surface area, so I don't want to have a v equals that I might accidentally like take the derivative of when I'm not supposed to. All right, so this guy is my constraint. The objective function that we're trying to optimize is surface area. So the surface area of a box is the area of all the surfaces. This box has a bottom, so x times x is x squared, and it has 1, 2, 3, 4 sides. The dimensions of each of those are x times y. Normally a box also has a top, but we're told that this one has an open top. So our surface area, x squared plus 4xy. All right, that's what we're trying to optimize, to minimize in this case. So we want to take the derivative of that. But first we use our constraint to write the objective function in terms of one variable. So my x squared y, I'm going to solve for y is equal to 216 divided by x squared. And that guy gets substituted over here for y. So surface area is equal to x squared plus 4x times 216 over x squared. And let's simplify before we take our derivative. One of those x's cancels out. So surface area is equal to x squared plus 4 times 216 is 864. And instead of leaving that x in the denominator, because I know the next step is to take the derivative, I want to write it as x to the minus 1. That's going to make my derivative step just, a wee bit easier. So that's what we'll do. Let's take our derivative. The derivative of surface area is 2x. Now bring the negative 1 exponent down, becomes minus 864 x to the negative 2, and then we'll set that equal to 0. So 2x, now if I'm solving this equation, instead of leaving it with a negative exponent, it's going to be easier to write it back into the denominator. So I want to bring the negative exponent up when I'm taking derivatives. I want to pop it back down in the denominator when I'm solving. So 864 over x squared is equal to 0. And then I can multiply through by x squared on every term, and that's going to give me 2x to the third power. Actually, let me show that work. So I'm multiplying x squared there, I'm multiplying x squared there, and I'm multiplying x squared there. It's going to get it out of the denominator, making this solvable. 2x cubed minus 864 is 0. X cubed is equal to half of 864 is 432. Excuse me, that should be an x cubed. So let me fix that. I'm going to scribble it out so you can see my mistake. X cubed is equal to 432. So to solve this, we're going to take the cube root of both sides, or in your calculator, it's a little bit easier to write it as 432 to the parentheses 1/3 power. Okay, and let me come back over here for my answer. X is equal to, and I'm going to write this in decimal form, and let's go to 2 decimal places, 7.56 inches. So that the bottom dimension of the box is 7.56 inches. and then y, which is 216 over x, or over, now I know what x is, 7.56 squared. Let's see what we get there. When I type that into my calculator, I get 3.78. So at the x dimension is 7.56. The y dimension is 3.78 inches. And the question does ask me for the volume. So to get the volume, what is the surface area? Excuse me. The question does ask me what is that minimum surface area. So for that, I'm taking 7.56 squared plus 4 times 7.56 times 3.78. And there's another, just be careful when you push the buttons on your calculator problem. In my calculator, as long as I push the buttons correctly, I got 171.46 square inches, or inches squared. Okay, so that would be the smallest surface area given this constraint of our volume of 216 cubic inches. So my answers for this one are right there and right there. There we go. All right, so that is the end of the video. Hopefully that gives you some foundation to attack some of the homework problems. Let me know if you run into any that you can't handle. I can help you get started on them, post a little video in Blackboard, or see me during an office hour. Thank you very much for watching. Have a wonderful day.